Hello guys, and welcome to this lesson. In our previous lessons, we started a wonderful job on circular motion. We worked on the introduction into circular motion. Then we went on to derive, the formulas for angular and linear displacement and velocity. So today we are looking at how we're going to derive the formula for angular and linear acceleration. So now when we talk about angular and linear acceleration, what are we talking about? Don't forget we talk about angular and linear acceleration. Acceleration is simply the change in velocity over time taken. So let's see how we're going to derive the formula for linear and angular acceleration. So right here we have a circle like this. Let's assume that there's a ball. Maybe a ball. Let's say a ball is being weird. Now this is a string. Let me say this is a string. Now the ball is here at point A. Now the ball rotates like this, gets to point B also like this at this angle theta. So the ball is here at the very point, then the ball rotates down to the very point. Now, at the very point, don't forget that in our previous lesson we said at the very point, this ball has a velocity of v, let's say v. Then at point B, there's another velocity of this at point B. Now, don't forget that this is a uniform circular motion, and also we can say it's horizontal, motion. So now the fact is this: you also have an angular velocity, a velocity that is concerned about the angular movement of the very body, while this one talks about the speed of the very body at different junctions, at junction A and junction B. So how do we derive the formula for linear and angular acceleration? Now, there's it. For linear acceleration, now let's start with angular acceleration first. Now, for angular acceleration, angular acceleration is being denoted. We're going to see what we're going to use. We're going to use alpha to denote it. Angular acceleration, which I'm going to use alpha for. Angular acceleration is simply the change or delta, anyhow we can use delta to represent change, is simply the change in angular velocity, angular velocity over time taken. It's simply the change in angular velocity over time taken. That is what angular acceleration simply is. So when we talk about angular acceleration, now don't forget we're using alpha. So what's the change in angular velocity? Angular velocity is simply this omega over time taken. So now this angular velocity is in rad per second, that's radians per second. In our previous lesson we derived this and we got the zero unit, while time is in seconds. So it means angular acceleration is in rad per second squared. Whether you write it like this or that's a unit, whether you write it like this or you write it like this. So there's a unit for angular acceleration. Now this is the first formula for angular acceleration. Now we can also derive another formula for angular acceleration. Now look at this. Now, if you look at this, at this very junction, this is a tangential or linear velocity. You can see that at point A, at point B. Now, don't forget that now for the part that we're talking about circular motion, the angle involved, as this angular displacement, is very, very tiny, very small. So most times, another formula for angular acceleration can go to us. You can say it is simply the change in angular linear velocity over time taken. So it's simply the linear velocity or tangential velocity over time taken like this. Now, why is this so? It's so because of the fact that when you look at the fact that the angle involved as this thing rotates from here to here, as it rotates, very small angle. I mean, small angles are involved. And for the fact that small angles are involved, it simply means you can see it is change in not just velocity, not just linear velocity. I mean, angular velocity, angular linear velocity over time taken. So what does that mean? So angular acceleration, or we call it centripetal acceleration. Don't forget, this linear is seen as tangential, while this is angular or centripetal. So angular acceleration, the same thing as, although we have this, the theta that's angular displacement over time, this very angular stuff is angular displacement times v over 1. So d over this, which is, don't forget, angular velocity is angular displacement over time taken. So what do we have? Angular acceleration is simply this, angular displacement times time taken. That is what the angular times velocity, I beg your pardon. So angular acceleration is d omega. That's another formula we could use. We could use this. This is one formula here. This is another formula here. These two formulas are for angular acceleration. So quickly, let's write our formula for linear acceleration. So what's the formula for linear acceleration? Linear acceleration is very easy. For linear acceleration is simply the change in it's simply the change in linear velocity. It's simply change in linear velocity over time taken. So that's just that. Now, it's quite different from angular acceleration. If you look at the second formula for angular acceleration, it's not just change in velocity. It's change in velocity at a very tiny angle involved. And that's why we have this. So that's just after that. But these angular acceleration, we're going to use normal A acceleration. We're going to use this. Angular acceleration is change in velocity to just normal linear velocity over time taken. That is what it is. So now when you look at this, we know that acceleration is simply velocity over time taken. We've seen that already. So it's always a meter per second squared. So this is a basic formula for angular acceleration. And also, don't forget something. I want you not to forget something. Now, when you look at the fact that we have v equals to wr, when we derive in our previous lesson, when we derive a linear velocity, the formula for linear velocity. Linear velocity is written as angular velocity times the radius. So if we incorporate that here, so bring it here, let's see what we're going to get. This is one of the major formulas. So let's see if we incorporate that. V is WR like this over time. That's what the V is. Now if V is WR over time. Now look at this. Don't forget, this is angular acceleration. Angular acceleration is W over T. So we can see something like that here. There's omega over T now times R. So that means linear acceleration, apart from velocity over time taken, which is the most basic formula, it could also be this over this, which is angular acceleration times radius. So the same pattern being maintained. So angular displacement, linear displacement is equals to angular displacement, which is theta times radius. We saw that in our previous lesson. Linear velocity is the same thing as angular velocity times radius. And right now, we have the same thing. Linear acceleration is the same thing as angular acceleration times radius. So that's that for that. So here are all the major formulas we're going to be using, in our next in the calculation we're going to be seeing in the next couple of lessons. So we have everything set out. This is linear acceleration. Either this or this. You can use it out of the formula. This is angular acceleration, which is angular velocity over time taken, and also angular acceleration is the same thing as linear velocity times angular velocity. And we can also derive more formula. We can bring out more formulas on this. As you can see, this is v equal to angular velocity times r. So you can substitute the stuff in here to get more formula for angular acceleration. Angular acceleration is same thing as the velocity with the linear velocity is angular velocity times radius times angular velocity. So angular acceleration can also be assumed to be angular velocity squared times radius. As you can see, as easy as that. And also, we could also make we could make the W, that's omega, the set of formula. Say omega is linear velocity over radius. So that angular acceleration is going to be the linear velocity times linear velocity over radius. So angular velocity is linear velocity squared over radius. Now, whichever you want to use, they are all perfect formula. They are all perfect formula for angular acceleration. Either this or this or this or this. These are all the perfect formulas for angular acceleration. So that's that for this very lesson. So at this very point in time, we're drawing the curtain of today's lesson. If you found this lesson resourceful, please subscribe to this very channel at Edgy Mosaic, and also follow me on Facebook at Revelation Up. And please share this lesson with others in order to also help them grow just like the way you're growing. So see you in the next lesson. Thanks.